temperature. Let's go bigger.
Can we really believe all this though?
We ain't got no other choice.
Right.
I'm not gonna go up to a sun and say, let me check this.
Right.
What's up, folks?
What's up, you guys?
I'm Juan.
I'm Crystal.
Make sure you go hit that subscribe button and turn on those post notifications.
We post every single day.
And make sure you go comment down below what you guys want us to react to next.
So in today's video, we're going to be reacting to the largest star in the universe. I'm excited. Look, I say I'm excited every video, but this one I'm really excited for. Okay.
Look, we graduated high school in 2017. I'll be honest with you, I ain't seen nothing science related since.
Yeah, no.
So we about to dabble into this.
I mean, I did have an astronomy class.
Oh, you did in college, yeah.
Yeah, but I mean, I didn't really learn anything. So anyways.
I had a science class for 3 days and then in college. And then I was like, I'm not going to this class. Because I saw the syllabus and I was like,
Oh yeah, you dropped it. You dropped it.
We had to read like 5 books within the next 2 weeks. And I said, So I got a different class. Yeah, I think we both know that our star obviously isn't the biggest one.
Yeah, obviously.
Which is so crazy because it's so big.
It's huge. It's huge.
I said that.
What? So big.
Let's get into this video.
It's the largest star in the universe. And why is it that large? And what are stars anyway? Things that would like to be stars. We begin our journey with Earth.
Okay.
Not to learn anything, just to get a vague sense of scale. The smallest things that have some star-like properties are large gas giants or sub-brown dwarfs. Like Jupiter, the most massive planet in the solar system. 11 times larger and 317 times more massive than Earth, and more or less made of the same stuff as our Sun. Just much less of it. The transition towards stars begins with brown dwarfs, failed stars that are a huge disappointment to their mums. They have between 13 and 90 times the mass of Jupiter. So even if we took 90 Jupiters and threw them at each other, although fun to watch, it wouldn't be enough to create a star. Interestingly, adding lots of mass to a brown dwarf doesn't make it much bigger, just its insides denser. This increases the pressure in the core enough to make certain nuclear fusion reactions happen slowly and the object glow a little. So brown dwarfs are a sort of glowy gas giant that don't fit into any category very well. But we want to talk about stars, not failed wannabe stars, so let's move on.
Dang, you just threw them to the
Main
side?
sequence stars. Once large gas balls pass a certain mass threshold, their cores become hot and dense enough to ignite. Hydrogen is fused to helium in their cores, releasing tremendous amounts of energy. Stars that do that are called main sequence stars. The more massive a main sequence star is, the hotter and brighter it burns, and the shorter its life is.
Where was videos like this when it was time for our science test?
Exactly. That's exactly what I was literally thinking in my head. Like, I'm seeing all the eyes and stuff. Ours is boring. It made me go to sleep. Yeah. Honestly.
But
and then we were forced.
Let's not forget about Bill Nye though.
Oh yeah, Bill Nye.
Bill Nye, the science guy. Yeah, I know.
I love Bill Nye. That's the only time I stay awake.
Once the hydrogen burning phase is over, stars grow, up to hundreds of thousands of times their original size. But these giant phases only last for a fraction of their lifespan. So we'll be comparing stars at drastically different stages in their lives. This doesn't make them less impressive, but maybe it's good to keep in mind that we'll be comparing babies to adults. Now back to the beginning. The smallest real stars are red dwarfs, about 100 times the mass of Jupiter, barely massive enough to fuse hydrogen to helium. Because they are not very massive, they are small, not very hot, and shine pretty dimly. They are the only stars in the main sequence that don't grow once they die, but sort of fizzle out. Red dwarfs are by far the most abundant type in the universe. Because they burn their fuel very slowly, it lasts them up to 10 trillion years, 1,000 times the current age of the universe. For example, one of the closest stars to Earth is a red dwarf star, Barnard's star, but it shines too dimly to be seen without a telescope. We made a whole video on red dwarfs if you want to learn more. The next stage are stars like our Sun. To say the sun dominates the solar system is not doing it justice, since it makes up 99.86% of all its mass. It burns far hotter and brighter than red dwarfs, which reduces its lifetime to about 10 billion years. The Sun is 7 times more massive than Barnard's star, but that makes it nearly 300 times brighter
I always
with
wonder,
twice
like,
its surface.
How do people study stuff like this? You know,
Right.
Like, how do we learn and get this information? I mean, I would assume that it's just like a lot of watching, a lot of observation, calculations over the years to see if things fizz out. But he said they fizz out. The red dwarfs fizz out, but they live up to some many times more than the existence of the universe. So, like, how do you really know how they end if it obviously hasn't happened yet?
Right. I mean, maybe because, you know, I don't know, just like my opinion of what I think about it. I think because we go up into space so long, like so many times throughout like the years, and we take up with those rovers, you know, and different robots and stuff to actually take those type of pictures. So like God knows when they started doing this to even be able to know, you know what I mean?
Yeah.
Or they
It's
just
a lot
taking
of
a
observation,
you know, a scientific guess, you know? I don't know.
Temperature. Let's go bigger.
I think, can we really believe all this though?
We ain't got no other choice.
Right.
I'm not gonna go to a sun and say, let me check this.
Right.
This
No.
is 2 solar masses with a radius 1.7 times that of the Sun.
Man.
But its surface is nearly 10,000 degrees Celsius, making it shine 25 times brighter.
I didn't know
Burning
the exact
that hot
temperature.
reduces its total lifespan by 4
can
times
get that
to
close.
2.5
Maybe you don't have to
years.
get close to understand.
Stars
you know?
close to 10
Just be in a
times the
spaceship
mass
like,
of our
this is
Sun
how
have
it's
surface temperatures near 25,000 degrees Celsius. Beta Centauri contains 2 of these massive stars, each shining with about 20,000 times the power of the Sun.
I love these
That's
colors.
a lot of power coming from something only 13 times larger.
can't even see Earth
but they'll
no more.
only
Nope.
burn for about 20 million years. Entire generations of these blue stars die in the time it takes the Sun to orbit the galaxy once. So is this the formula? The more massive, the larger the star. The most massive star that we know is R136A1. It has 315 solar
Oh God,
masses.
I hope nobody named their kid that.
No, I swear to God, nowadays, bro, people would name their kid what, R134.
Its tremendous mass and power, it's barely 30 times the size of the Sun. The star is so extreme and barely held together by gravity that it loses 321,000 billion tons of material through its stellar wind every single second. Stars of this sort are extremely rare because they break the rules of star formation a tiny bit. When supermassive stars are born, they burn extremely hot and bright, and this blows away any extra gas that could make them more massive. So the mass limit for such a star is around 150 times the Sun. Stars like R136A1 are probably formed through the merger of several high-mass stars in dense star-forming regions and burn their core hydrogen in only a
said
few
probably.
million years.
Probably.
So this means they are rare and short-lived. From here, the trick to going bigger isn't adding more mass.
Something bigger than
To
that.
make the biggest stars, we have to kill them. Red giants.
Oh yeah. Great.
When main sequence stars begin to exhaust the hydrogen in their core, it contracts, making it hotter and denser. This leads to hotter and faster fusion, which pushes back against gravity and makes the outer layers swell in a giant phase.
Whoa.
And these stars become truly giant indeed. For example, Gacrux. Only 30% more massive than the Sun, it has swollen to
Holy.
about 84 times its radius. Still, when the Sun enters the last stage of its life, it will swell and become even bigger, 200 times its current radius. In this final phase of its life, it will swallow the inner planets.
How old is the Sun?
And
How
if you
much time
think
we
that's
got?
impressive,
Oh
let's
God,
finally
it is
introduce the
2020, huh?
largest stars in the universe,
Oh God.
hypergiants. Hypergiants are the giant phase of the most massive stars in the universe. They have an enormous surface area
let's see how big this
that
thing
can
gonna get.
radiate an insane amount of light. Being so large, they're basically blowing themselves apart, as gravity at the surface is too weak to hold on to the hot mass which is lifted away in powerful stellar winds. Pistol Star is 25 solar masses, but 300 times the radius of the Sun, a blue hypergiant aptly named for its energetic blue starlight. It's hard to say exactly how long Pistol Star will live, but probably just a few million years. Even larger than the blue hypergiants are the yellow hypergiants. The most well-studied is Rho Cassiopeia, a star so bright it can be seen with the naked eye, although it's thousands of light years from Earth. At 40 solar masses, this star is around 500 times the radius of the Sun and 500,000 times brighter. If the Earth were as close to Rho Cassiopeia as it is to the Sun, it'd be inside it and you would be very dead. Yellow hypergiants are very rare though, only 15 are known. This means they're likely just a short-lived intermediate state, as a star grows or shrinks between other phases of hypergiantness. With red hypergiants, we reach the largest stars known to us, probably the largest stars even possible. So, who's the winner of this insane contest? Well, the truth is, we don't know. Red hypergiants are extremely bright and far away, which means that even tiny uncertainties in our measurements can give us a huge margin of error for their size. Worse still, red hypergiants are solar system-sized behemoths that are blowing themselves apart, which makes them harder to measure.
Right.
As we do more science and our instruments improve, whatever the largest star is will change. The star that is currently thought to be a...
I was thinking about that, like, if you think about science throughout the history, things get corrected because we get better technology, or we develop better technology over time. Like, I remember hearing something about, like, during the Renaissance era, which is like a little after the Middle Ages, that takes place in Italy. People believe that you emitted light from your eyes, and that's how you were able to see in the dark. But it wasn't until later on when they figured out that we actually perceive the light different. We actually perceive the light and absorb the light with our cones or whatever, rather than emitting it. You know what I mean? And so imagine, like, people just like, what? You know? And so it's like all the science stuff that we looking at now could very well be wrong.
Yep.
And you just kind of wonder, like, how many things do we do now that is just extremely flawed, where people in the future will look back at us and just laugh, like, never know.
Never know until it happens.
Among the largest we've found is Stephenson 218.
Who?
It was probably born as a main sequence star a few tens of times the mass of the Sun and has likely lost about half its mass by now. While typical red hypergiants are 1,500 times the size of the Sun, the largest rough estimate places Stephenson 218 at 2,150 solar radii and shining with almost 500,000 times the power of the Sun.
And when they say infinite
By comparison,
space,
the Sun seems like a grain of dust.
I mean,
our brains don't really have a way of grasping this kind of scale. Even at light speed, it would take you 8.7 hours to travel around it once. The fastest plane on Earth would take around 500 years. Dropped on the Sun, it would fill Saturn's orbit. As it evolves, it will probably shed even more mass and shrink down into another hotter hypergiant phase, accumulate heavy elements in its core before finally exploding in a core collapse supernova, giving its gas back to the galaxy. This gas will then go on to form another generation of stars of all sizes, starting the cycle of birth and death again to light up our universe. Let's make this journey again, but this time without the talking. The universe is big. There are many large things in it.
Look at us. Oh, well.
y'all feel insignificant yet?
Look at that. Look at that. We're a speck of dust. We are a speck of dust.
I think
A speck.
smaller than that. We the atoms that
We're
make
the
up
atoms?
dust particle. But I guess I'm not supposed to, but I just can't wrap my head around infinite anything. Everything on Earth has an end. Everything. There's nothing on Earth that infinite. So it's like it's hard to wrap your head around the process of infinity. So it's like it's hard for me to believe that, even though it has to be true, it's just that it's infinite space. There's just so much space, because it's like, let's say hypothetically space does end. Let's say you got this huge space, all these tiny little galaxies and these quadrants and these bigger, all these quadrants and galaxies.
It keeps on going out.
You know, if it does end, what's on the other side of that?
Exactly.
It can't be. It's just infinite space.
But,
there's just You know what I mean? You see how it don't make sense?
Yeah.
Like it just don't stop. It just go forever. Like how is that possible? How could it be something if it doesn't end? How is it infinite? Comment down below y'all thoughts, man. Comment down below what you guys want us to react to next, and make sure you hit that subscribe button. It's free, baby.
Just click the button.
It's alright. We won't tell nobody.